So the derivative for functions at a fixed number A is f prime of A is equal to the limit as h approaches 0 of f of A plus h minus f of A divided by h. If we let A vary, we replace A by x, which is a variable. Then the derivative is, so f prime of x is equal to limit as h approaches 0. The formula should be very much the same, right? You just replace A by X. A is a fixed constant, X is a variable. You can substitute anything into the place of X, right? So f prime of X is limit equal to the limit as h approaches 0 of f of X plus h minus f of X over h. Example, find f prime of X given f of x is equal to x. Right, so for example, let's try to find the derivative of the function f of x equal to 2x. Very simple at first, right? Then we can go over something else more difficult. So use the formula, right? So f prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x divided by h. So you have f of x plus h is, so this limit as h approaches 0 of x plus h minus f of x is just x divided by h. So x, negative x cancel out, and you're left with limit as h approaches 0 of h over h. H over h is just 1, so limit of 1 is 1. So let me all right, so next, find f prime of x given that f of x is equal to x squared. All right, so using the formula, the same formula, right? So f prime of x is the limit of f of x plus h minus f of x divided by h as h approaches 0. So f of x plus h is x plus h squared minus x squared divided by h. So this is what you have, limit as h approaches 0 of x squared. So I'm going to expand the x squared plus h squared. Because once again, if you direct substitution and let h equal to 0, you're going to have 0 over 0. That's indeterminate form. So you have to somehow eliminate h in the denominator. So here I expand x plus h squared. I have x squared plus 2xh plus h squared minus x squared divided by h. This is a side note here, right? So the function is f of x equal to x squared. For f of x plus h, I'm just going to substitute or replace x with x plus h. So x squared cancel out, and you're left with limits as h approaches 0 of 2xh plus h squared divided by h. Right. So h as the common factor on the numerator, you have limit h approaches 0 of h times 2x plus h divided by h. You make the cancellation here. When you let h approach 0, you have 2x for the answer. Okay, so the next example is find f prime of x given f of x is equal to square root of x, right? Then determine the domain of f of x and f prime of x, right? There should be something very interesting from the domain of the function and the derivative of the function. So first, let's find the derivative of the function f of x equal to square root of x. Right, so f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Right. So f of x plus h is square root of x plus h, and then f of x is just square root of x. So this is minus square root of x divided by h. If you use direct substitution, once again, you have 0 over 0. Right? You don't want that. So you have to radicalize this particular function. So to do that, I'm going to multiply the top and bottom by x square root of x plus h plus square root of x. Right. Because somehow I want to eliminate h in the denominator. Okay. So I have limits as h approaches 0 of square root of x plus h square minus square root of x square. Right, so right, the numerator is just the difference of 2 square. And then in the denominator is h times square root of x plus h plus square root of x. So I got limits as h approaches 0 of x plus h minus x over h times square root of x plus h plus square root of x. All right, so x minus x cancel out, and you're left with limit as h approaches 0 of h over h times square root of x plus h plus square root of x. Now h cancel out, you get when you let h go to 0, you're going to have 1 over square root of x plus square root of x. I got 1 over 2 times square root of x. You find the derivative of the functions f of x equal to square root of x, right? So the derivative is equal to 1 over 2 times square root of x, right? So now the next question is to determine the domain of the functions, right? The domain of the function and the domain of the derivative. So f of x is equal to square root of x. So so the domain, right? Right, so hopefully you still remember this, right? So the expression under the square root has to be non-negative. Right? So x is greater than or equal to 0, or if you use the interval notations, you have 0 to positive infinity. For the derivative, f of x is 1 over 2 times square root of x, right? You also have square root of x, but square root of x now is in the denominator, right? So square root of x, this expression and the square root of x is greater than or equal to 0, but it's in the denominator, so you do not want to include 0 in your domain, right? Or, right. So you can see that the difference between the domain of the function and the domain of the derivative. So there are many ways to write use notations of derivative, right? So you see one of the notations is f prime, right? That's a very common notation to use for derivative of your functions. But there are many more in mathematics that you can use as well. Depends on the person, it depends on the textbook that you read, the notations of derivative. Right, so consider the functions. Y equal to f of x, the first notations, y prime equal to f prime of x, where you use prime to indicate the derivative. Y is prime because this is the first, we call this the first derivative because you take the derivative of the function once, right? If you have to take another derivative or the derivative of the derivative, you call that the second derivative. I'm going to talk about that as well later on. There is also, this is dy dx equal to df dx. This is the Leibniz notations. So this dy dx or df dx, either one should be fine. This is not a fractions, right? So a lot of people confused about this notation. This is not a fractions. So you see the way I say that dy dx, I didn't say dy over dx, right? So dy dx means that I'm going to apply the derivative on y, or I want to apply the derivative on f, right? Or in other words, the way to write is ddx of y or ddx of f, right? For ddx is differentiations operator, right? So you apply this operator on a functions, right? So therefore, dy dx or df dx is not a fractions. Right, so just be careful with that. And now the notations you might want to know is d of f of x, right? So capital D in this case is also a differentiation operator apply on the function f of x, or d sub x of f of x, right? It's indicate that I want to find the derivative of the function with respect to x. So these are the few notations that you might want to know. So most of the time, I'm going to use this notations, prime notations, and the Leibniz notations, dy dx or df dx. If you want to evaluate a derivative at a point x equal to a, what you can do is you can have f of a, or you can use y prime of a, f prime of a, or y prime of a, or if you use the Leibniz notations, you have dy dx. Like the vertical lines indicate that I want to evaluate that dy dx at x equal to a, or I want to evaluate df dx at x equal to a. Right, so the vertical line indicate that I want to evaluate. Like, let's evaluate the function at that given points. So let me quickly introduce differentiable function. So a function f is differentiable at a if f prime of a exists. When I say differentiable, I mean you look at the function, the smoothness of the function. It could be continuous, but it may not be differentiable. Right, so that's the definitions of the functions as a differentiable function. Theorem. For this theorem, differentiability implies continuity. If you have a function that is differentiable at that point, then the function will be continuous at that given point as well. So if f is differentiable at a, then f is continuous at a. All right. So that is a very strong statement, right? So if f is a differentiable at a, then f is continuous at a. However, the other directions may not be true at all time, right? I just want to make a quick note here. The reverse statement is not always true. Right. It could be, but it does not always. It's not always true. Okay. For example, right, once again, differentiable means smoothness of the curve. If you have the absolute value of absolute value function, for example, let me quickly draw the absolute value function. Right, so y x 0, y equal to absolute value of x. So this function, absolute value of x, is continuous at the point x equal to 0, obviously, right? But it is not differentiable because it's not smooth at that point. We can mathematically prove that is not differentiable, but by looking at the graph, you can see that that is, akin, right? So that is not differentiable at the point x equal to 0. So here, this example, y equal to f of x, absolute value of x is continuous at x equal to 0, but it is not differentiable at x equal to 0. Right. There are some functions that if the function is continuous, then it's differentiable. It's possible, but it's not always true. It's not always the case. So that's why in this theorem, I just have one direction of the theorem. I say that if f differentiable, then for sure f is continuous at that point. So that's a quick example to indicate that sometimes the function can be continuous at the given point, but not differentiable at that point. All right. A function, when the function failed to be differentiable, when a function failed to be differentiable. So there are three cases. I'm going to draw something to you first, and then I'm going to write down the name. For example, I have this type of function. So when you have a corner or a kin, then that is not differentiable. For the second case, there are three cases. So for the second case, when you have any discontinuity, right? So if you have discontinuity, then it's not differentiable. Then the last case, when you have a vertical tangent line, so something like that. This is the vertical tangent line. So example, given the graph of f, state with reasons the numbers at which is not differentiable. So let's take a look at this graph. Right, so there are three cases when the function is not differentiable. The first one, if there's a corner or kin, if there's any discontinuity, or if you have the vertical tangent line. For this, the functions is not differentiable when at x equal to -1, x equal to 2. So there are two cases for this particular example. At x equal to -1, the reason is that this is a discontinuity. Jump discontinuity. At x equal to 2, there's a hint or corner if you want, and therefore the function is not differentiable. So for higher derivatives, right, so whatever you have so far, it's just the first derivative, so you can move on to higher derivatives. Consider y equal to f of x. Then the second derivative, you can have is y double prime or f double prime of x. Or what you can do in terms of Leibniz notations is d dx of dy dx. You apply another differentiation operations on dy dx, where you can write d squared y dx squared. So that's the notations. Another notations for the second derivative is f sub xx, right? So if you have f sub x, that's the first derivative with respect to x. Fxx is the second derivative with respect to x. With respect to that's some notations that you can use. For the third derivative, you have y triple prime equal to f triple prime of x, or d dx of d square y dx square. Right, so you apply another differentiation operations on the second derivative, you get d cube y dx cube. Right, so that is the the third derivative. Right, so, or you can write fxxx. Right, so there are 3x for that. For the nth derivative, what you can write is y to the n, or f to the n of x to indicate this is the nth derivative. Or, oops, what you can have is dny dxn. Okay, that's some of the notations for the higher derivative.